Have you ever stood at the bottom of a giant skyscraper and wondered how something so tall and heavy can possibly stay standing? Now imagine the very ground beneath it suddenly starts to shake violently, like a rug being pulled out from under it. How does it not fall? We live in a world of incredible structures. Cities reach for the sky with towers of glass and steel, monuments to human ingenuity. We build them on what seems like the most solid thing we know, the earth itself. We trust the ground to be still and strong. But in many parts of the world, that trust is broken. The ground moves, shifts, and rips apart with unimaginable force. This creates a massive problem for engineers. How do you build a city that can withstand an attack from the planet itself? To understand the solution, you first have to understand the sheer violence of the problem. An earthquake is not just random shaking. It begins deep underground, where tectonic plates grind against each other. When they slip, they release a colossal amount of energy in waves. The first waves, called P waves, are fast. They shoot up to the surface, jolting the ground vertically up and down. For a building, this is like being punched from below, but the real danger is yet to come. Next are the S waves, or shear waves. These are slower, but far more destructive. They move the ground horizontally, from side to side. Imagine trying to stand still while someone yanks the floor left and right. That's what a building experiences. A traditional building made of brick or concrete is rigid. It's designed to resist the downward pull of gravity. When its foundation is thrown sideways, the top of the building tries to stay put because of inertia. This creates enormous stress. The base moves one way, the top wants to stay, and the middle is stretched and bent. If the shaking is strong enough, the structure simply cracks and crumbles. It cannot handle this sideways force. But the problem gets even worse. Every building has a natural frequency, a rhythm at which it likes to sway. If the earthquake's waves happen to match that frequency, the building's swaying gets amplified with each shake. This phenomenon is called resonance. The gentle sway becomes a violent thrashing, tearing the building apart from the inside out. And the ground itself can betray the building in another way. In some soils with high water content, the intense shaking can cause something terrifying called liquefaction. The solid ground temporarily turns into a thick, unstable liquid, like quicksand. A building's foundations, which once rested on solid earth, are now floating in a soupy mix. The structure can sink or simply tip over. So you have vertical jolts, violent side-to-side shearing, the building's own resonance working against it, and the ground potentially turning to liquid. Faced with this incredible list of challenges, the first engineering approach was simply to make buildings stronger. They used thicker columns and more steel. The idea was to fight the earthquake with brute force and rigidity. But this often just made things worse. A stiffer building can attract even more force from the earthquake. The old way was a mistake. Then, engineers had a breakthrough insight. What if instead of fighting the earthquake, you just get out of its way? The mistake was thinking a building had to be a rigid rock. The insight was to see it as a flexible system that could absorb or redirect energy. Don't fight the force. Don't try to stand still. Instead, learn to go with the flow, to dance with the earth. This single shift in thinking changed everything and led to the amazing life-saving technologies we see in modern building. The first solution is called base isolation. The building is essentially disconnected from its own foundation. It's placed on flexible pads or bearings made of steel and rubber, which act like a suspension system. When the ground shakes, the isolators move, but the building above stays almost still. Another solution is to add dampers, which are like giant shock absorbers. Some are huge pendulums near the top of the building, called tuned mass dampers, that swing in opposition to the building's sway to cancel it out. Others are pistons filled with fluid that absorb the shaking energy and turn it into heat. So the next time you see a skyscraper, remember it isn't strong just because it's big. It's strong because it's smart, designed not to resist nature but to wisely respect its power.